proton moving in a horizontal circle. Drawn a top view of that. And under the influence of a uniform magnetic field. So the magnetic field is the only thing that's exerting a force on it. And it's going counterclockwise around the circle. So this does indeed represent an instant in time. An arbitrary position, to be sure, but an instant in time while this proton is moving around in the circle. Now, for it to be moving in a circle counterclockwise, there's got to be a leftward force at this point, or westward force, if you will, toward the center. Otherwise, it'll move along a straight line path. So there will always be a center-directed force acting on it, and of course the only thing that is exerting a force on the proton is the magnetic field, so we need a center-directed force exerted on the proton by the magnetic field. It will always be a leftward-directed force, where leftward is with respect to the straight-ahead direction, the direction in which the proton is traveling. So when it's going over this way, from our point of view, it will be downward, but from the proton's point of view, if that's the forward direction, it will be the leftward. In order to get a center-directed force or a leftward-directed force by the right-hand rule, let's say if we point our fingers, I'm looking at F is equal to Q times V cross B. And for a positively charged particle, the force is going to be in the same direction as V cross B, because you multiply that vector sign, you get a vector in the same exact direction. Now, if I point my fingers in the direction of V, I'm supposed to close my fingers and have them point in the direction of B, the second vector. And if I do that, I'm supposed to get the thumb pointing in the direction of F. Now, what I'm missing is the middleman. So I'll arrange my hand so that the answer is to the left. I've got my thumb pointing to the left with the fingers pointing in the direction of V. And now if I close my fingers, they tend to point in the downward direction. So B must be in the downward direction. So I'll go ahead and draw the magnetic field in there. Downward is represented by end of the page here. There's my magnetic field. Do a quick test on that. Point the fingers in the direction of V, arrange the hands so that if I close the fingers, they point in the direction of B, and yet the thumb points to the left in this picture. And if it was up here with V going in that direction, if I arrange my hands so that the fingers were pointing in that direction, and then still the palm directed exactly downward, which in this case is into the screen, the thumb would point toward the bottom of the screen, which would be again toward the center of the circle. So no matter where this particle is, try it over here, be that way, arrange the hand so that the fingers are pointing toward the bottom of the screen, palm facing into the screen so that if I close the fingers point in the direction of B, the thumb being to the right of the screen, which is still toward the center of the circle. So no matter where this particle is on the circle, it's got a velocity tangent to the circle, and it's going to result in a force exerted on it by the magnetic field toward the center of the circle. And because the circle is horizontal and the magnetic field is vertical downward toward the center of the Earth, they're at right angles to each other. So the force, which is in general QV cross B, has a magnitude which is just given by QVB, whereas normally it would be QVB sine of theta. The angle between V and B is 90 degrees, sine of 90 is 1. The way I like to look at it, when they are exactly perpendicular, is just the product of the magnitudes. The cross product in magnitude is the product of the magnitudes of the vectors. Okay. They're looking for the magnitude and the direction of the magnetic field. Let's try a free body diagram for this object. There's the proton, got one force acting on it. F, which is the QVB, and it's got an acceleration directed toward the center of the circle, which, because it's moving in a circle at constant speed, notice with the force always being perpendicular to V, it's never going to cause V to increase or decrease. So A is the centripetal force that an object in uniform circular motion experiences. Actually, an object in circular motion experiences where V is the velocity at an instant. But in this case, V is staying the same throughout the whole trip. So I'll do a sum of the forces, that is apply Newton's second law, looking at this free body diagram. Sum of the forces to the left, S, times the acceleration to the left. So F is equal to ma. We only have the one force to the left, and our acceleration to the left is what I called A. QVB then is mv squared over r. One of the v's cancels, and I'm looking for b, so I'll divide both sides by q. I've got b is equal to mv over rb. Sorry, over rq. Divide both sides by q. Go ahead and substitute values. The mass of the proton, got to look that up. It's given as 1.6726 times 10 to the minus 27 kilograms. Uh, 442 meters per second for the speed. R is 0.380 meters given in the problem, and the charge on a proton is 1.60 times 10 to the minus 19th coulombs. I do want to check on that radius. Yeah, there it is. Radius 3.80 meters. Plug those into the calculators, evaluate, you get 1.2159 times 10 to the minus 5th Tesla, which rounds off to, move that decimal over and I get 12 point, and that rounds off to a 2. So I've multiplied by 10, I got to divide by 10, making that a minus 6, or microtesla. 12.2 microtesla. And I give the direction as well. B has both magnitude and direction. And when I give both the magnitude and direction, I'm given the properties of a vector, how big it is and which way. Alright, that marks the end